line integral, I'm doing a three-dimensional version. So f is a function of x, y, and z. And we're doing this line integral over some three-dimensional curve. And it's basically just replace the x, y, and z by their parametric equations in terms of t, and then differentiate, square, and add, and you got this guy, and you stick a dt. And that's basically it. So I'm going to do a couple more of this, and then we'll move on and we'll show you some other different types of line integrals and the usage for them. In other words, what does this get you? Because it is a number when it's finished, right? What is that number representing? And you'll find out that it's actually representing the work done in moving through a force field. Kind of interesting that it does that. So who have I got? Okay, so I have got this integral. This is a version of question 6. If you were doing the homework already, I have moved the questions, the order around, but I haven't removed any questions. So if you go and you say, what happened to my question 6? It might now be called question 8, but it still will be there. And if you did it, it still would have been graded. So here is our curve in 3D. Right? We would call that a space curve. In fact, it's not uncommon, if you remember 141, 163, that you might write it like that. You remember those space curves? Three-dimensional curve, right? That guy. So this information can be written like that. So that's just a convenience. In fact, that's a little bit less work than that. So anyway, we have, what am I doing today? X, Y, Z. Focus. I think it's that banana joke still in my head. So we have X, Y, Z, this guy, right? So there's our line integral. X, Y, and Z get replaced by these three guys. Then you multiply by this dt. So, and in this question, they told us that t is going from 0 to pi, which is nice of. So it's going to be the integral from 0 to pi. X, which is 3 sine t, y, which is t, z is -3 cosine t, square root, here we go, dt. If you differentiate this guy, you get 3 cosines, and if you square 3 cosines, you get 3, gets you 9 cosine squareds. Differentiate this, you get 1, and if you square it, you get 1. Differentiate this, you get +3 sine t, but then you square it and you get +9 square t. Are we comfortable with all this goes here and that goes there? Right. Now you would expect, or at least hope, that this will turn into something a little bit nicer. So I have -9 t, sine of t, cosine of t. Do you recognize that these two guys play well together, don't they? What does 9 cos square t plus 9 sine square t get you?
9.
Yeah, well, 9 plus 1, you're right, and that gets you square root of 10. So we got this guy. So all I'm going to do right now is work on how to get this integral. There's at least 2 different ways to do this integral, but the way I'm going to do is, I think, for me anyway, most obvious. I'm going to pull out that -9 and square root of 10, just to tidy things up a little bit. The biggest problem that you've got here is that there's 3 things multiplied, and that almost always means that you have to do something algebraically to it. Because if you try doing u subs, it won't work. If you try and do integration by parts, oh, we want to go there, right? So I'm going to do a trig identity. And sine t cosine t is the same thing as a half of the sine of 2t. I'll come back to that in a minute. I'll pull out that half with all the other stuff. So what I've managed to do is take these three things and convert them into two things. Now to try and prove it to you. Sine t, cosine t with a 2 in the front is the double angle that you got from 141 trick. If you half both sides, divide both sides by 2, you now can replace a single sine t by that a half. You comfortable there where that half came from? This guy is that fella. Then I just pulled out the half, and now we're left with this. And this is a point where I feel I can get away with dot, dot, dot. What method from Calc 2 would you use to integrate a t times sine of 2t?
That looks very much like an integration by parts.
And it is, right? And you'd make that the first fella, that'd be F, and you'd make this the second guy G. And if you do the UDV thing, you know how that works. We comfortable with that one? But it's those little pieces of knowledge like that is this fella. It's those little pieces of knowledge that are kind of the key to doing this. See, if you didn't recognize that or didn't even think of that as a thing to do, wouldn't you kind of just go there and say, oh, I don't know, I give up, right? You know it's doable, except for that one bloody question yesterday, which I had another 20 minutes looking at and I still couldn't make it work. So as much as I don't want to say it, I think it had to be a mistake. Still bugging me, but whatever.
You do wonder where the proofreader was.
Oh, you got to be fair with them. I mean, there's thousands of questions. So there's always going to be a couple. And what sometimes happens isn't even the guy's fault. He changes the question, but no one tells, you know, the other guy that the question has changed. So it is what it is. Right, so I want to show you, that's the end of that kind of question. I want to show you a new guy. And it's a special kind of line integral, and they're written like this. That is a line integral. Now, you've probably never seen a line integral written with a dx and a dy in. And P and the Q are just placeholders. P and Q are just functions of X and Y. So it could be X plus Y here and X squared here, right? So that is a generic line integral written in terms of these guys. So this one is written in terms of what we call the differentials. So this is a line integral in its differential form. So instead of a ds form, it's now this fellow, right? So how on earth do we do that? Well, let's give you an example and show you how you do it. If I try to write down the formula, you know, something like that, it wouldn't make sense. I mean, it would just be downright ugly because it'd be hard to really state it in a way that would, in my opinion, would make sense. So let's do a question. Let's suppose we're going to do x squared y dx plus y cubed dy. And that guy there is basically P and that guy's Q. P and Q contain X's and Y's or just X's, or it could be numbers, right? So there could be P and Q could be anything, right? And over C. And we are told that C is in parametric form again, is 2t squared plus 1, and y is 4t. So what I'm going to do is I'm going to take this line integral, the differential form of it, and I'm going to convert it into an integral in terms of t. Oh, and you need to know what t is. So t was from 0 to 1, right? So it's going to be the integral from t equals 0 to 1. X squared is going to be 2t squared plus 1 squared times y, which is 4t. And I'm going to write this line down for a minute, dx, plus a y cubed, which is 4t cubed, dy. So all I need to do now is figure out how to rewrite dx and dy in terms of t, right? let's show you how you do that. You'll be amazed how easy it is. I'll start with the information that connects x and t together, right? If I differentiate x with respect to t, I get 4t. Great. That makes sense? Now, this notation lends itself really well to this process. Can you see how I've rewritten dx in terms of t? Now, if you take the other guy, which is him, and you differentiate him with respect to t, you get that. And if you do a little crossover thing, I mean, we do that a lot in Calc 2, didn't we do a lot of that in USUBs? Right, it's the same thing, right? It's the same math, if you like. So returning back to the original, which is this fella, it's now the integral from 0 to 1. Might as well FOIL that out while we're at it. 4t to the pole, 4t squared plus 1 times a 4t. Replace the dx by another 4t dt plus this guy, which is 64t cubed, and replace the dy by a 4 dt. And now it becomes the integral from 0 to 1. I'm pulling that dt out like it was a common factor. And I've got all of this, which is 16t squared times that. So 64t to the 6, 16t times that is 64t to the 4 plus 16t plus 256 t cubes. So I'm just distributing all that, bringing this guy into the game. And basically, don't we just have a very long polynomial in terms of t?
That third term end up being 16t squared?
This one here? Agreed. Wouldn't this just be some ridiculously ugly power rule and 850, 3009, whatever? You get your answer. So the differential form of a line integral still becomes a single integral with respect to t, and we just have to add in, how to convert the dx and the dy into the t's. So far, so good. Can you imagine how difficult it would be me to describe what I just did in general terms? Because aren't P and Q going to be different each time? Aren't the X and Y parametric equations going to be quite different? And it's doable, but I'm not writing the formula down. It doesn't bring anything to the party. In fact, it confuses things. So before I do the next question, I'm going to remind you of something you did a way back in Calc 3. And that is how to find the equation of a line in 3D space. So suppose I have a point P with coordinates 1, 0, 3, and a point Q 2, -1, 4, right? And I want to find the equation of the line from P to Q. And not only do I want the equation of that line, I want to also know the start value and the finish value of t, because I only want to use that bit of the line. Okay. Step 1 to finding the equation of this piece of the line is you find what's called the direction vector. And I like to call that guy V. What is the direction vector of this particular line segment? How do you find the direction vector?
Subtract the Q components from the corresponding P components, so you get 1, -1, 1.
Correct. In other words, find the vector P to Q, right? And 2 take away that guy gets you 1, -1, and 1. So far, so good. Now, the X, the Y, and the Z components, right? The parametric equation of this line is, okay, I might try to remember what we called it. I remember. X naught plus AT, Y naught plus BT, and Z naught plus CT, where A, B, C are the components of this vector. Right? And X naught, Y naught, and Z naught aren't the X, Y, and Z coordinates of the starting point. In this case, we're going from P to Q, right? And it's important that you start with this guy and finish with that guy, because as you travel through a vector field, it's important that you know where you start and you finish, because if you switch places, isn't it the difference from going uphill and coming downhill? The numbers may be correct, but they'll not be the right size, right? They'll switch sizes on you. So in this question, the X is 1 plus 1t. The Y is nothing, minus 1t. And the Z is 3, add 1t. And in space chord form, because that's a much more convenient way to write it all down, we have that. Are we good with that? So we've got the equation, and basically that was step 1. And that was step 2. Right. Now that we know how to do that, it was so I could do question 7. We have a line integral of z squared dx plus x squared dy plus y squared dz. The curve is described as the line joining P, which is 1, 0, 0, to Q, which is 3, 1, 4. And now I need to go back here because I forgot to mention something. Didn't I ask, or I say, look, we need to know the T, the start and the finish. The start's 0. If you plug in 0 here, don't you get this guy? What value of T do you need to plug in to get Q?
1.
Yeah, and that's going to be nice and easy, right? So back to this question. From here to here, right? So first thing I'm going to do is I'm going to find the parametric equation of the line going from P to Q. And it's going to be pretty much a carbon copy of what I did here. The direction vector is the vector joining P to Q. So 3 take away 1 is 2. 1 take away nothing. 4 take away that guy. We got that. The X, Y, and Z for this straight line are going to be 1 plus 2t, nothing plus 1t, nothing plus 4t. Are we all comfortable with that? And won't t start at 0 and t finish at 1? Are we comfortable about that as well? So this question has now really changed a little bit. It's still the line integral in differential form of this. But we now know the parametric equation for x, y, and z, and we know the start and finish of these guys. So it's going to be the integral from 0 to 1. Instead of z squared, it's going to be 4t squared dx. Instead of x squared, it's going to be 1 plus 2t squared dy. And instead of y squared, it's going to be t squared dz.
I have a question.
Yes.
How do we know it's from T0 to T1?
Oh, T0 always gets you the start number.
Okay.
And the way this has been generated, if you plug 1 into here, 1 plus 2 times 1, 1, and 4 times 1, it gets you the second one. So
Okay.
if you do the equation of a line from P to Q, T equals 0 will get you P, and T equals 1 will get you the Q every time. So it's not just, well, this time it happens to be that, but the next time it's different. The only time that that would not be true, and I would never do it, is couldn't you use a direction vector 6, 3, 12 because you felt like it? Right. In other words, make a direction vector 3 times this one. That would also count as a direction vector, but that would screw up the 0 1 time. So don't do that. I mean, okay, if you get a half, a third, and 4/5, just live with it, right? Now, we still have to do, and I'll put it in different colors. We have to find out what dx is, dy is, and dz is in terms of t, right? If you differentiate a straight line like that, don't you get the answer 2? And that ends up being 2 dt. And this one ends up being 1 dt. And this one ends up being 4 dt. Are you comfortable about where these 3 guys came from? Right. So returning back here, I'm going to have 16t squared times 2 dt. I'm going to have a 1 plus a 4t plus a 4t squared times 1 dt. And I'm going to have a t squared times a 4 dt. So I'm now going to 0 to 1. I'm going to have 32t squareds plus a 1 plus a 4t plus a 4t squared plus a 4t squared dt. What have I got? That guy, and that guy gets me 40 t squareds plus a 4t plus a 1. And at that point, I'll finish. So a line integral written in its differential form, which is in this form here, still gets turned into parametric, right? Still gets turned into t's, but you have to approach it a different way, right? It doesn't have any square roots of this guy squared and so on, right? Any questions?
No.
Right. Then we are now going to look at yet a third version of how line integrals are written. And we're going to do, I'll put this somewhere here. We're now going to, this is the final version. The dot product version of a line integral. Before I even get into the, an example of this, let's do something at the side. From 163 you could have a space curve written like that. You remember the space curves in Math 163, right? That represents a curve in 3D. Now, if I asked you to find the derivative of this guy, I hope you would all say, well, it's easy to differentiate a space curve. Now, I'm going to use a different notation for the derivative. Would you agree that would be a rather clunky way of saying that? Great. But it still means that. So far, so good. Now, if you do a little cross multiply thing, you get that. Great. Now, this dt is going to be brought inside and given to each of the terms. And this guy is just called dr. So what we are looking at here is basically a differential in 3D. Do you see it's made up of 3 components, each with their own baby dt's? In a way, isn't it kind of what we've been doing for the last 2 questions, but not writing it in that format? So what does a line integral in dot product version look like? It looks like this. A vector field dot product with the differential. So in this story, you are going to be told who your vector field is. Remember those little vectors in 3D at any point x, y, z, there's a kind of direction that it's moving. So your force field, right, that guy there, I'm just going to call him P, Q, and R. So P would be some function of x, y, and z, so will Q and R be. Our d of R is basically going to be the derivative of x dt, the derivative of y dt, and the derivative of z dt. And so this fella essentially is, okay, from t equals a to b, this guy becomes the integral from t equals a to t equals b. If you do a dot product, don't you just multiply the x's together, added multiply the y's together, add, you multiply the z's. So in the format that I've got here, it's going to be PQR dot product with this stuff. So far, so good. And basically, I'm trying to create this formula that we're going to jump to. So if you do a dot product, you're going to have P times x dash of t plus Q times y dash of t plus R times z dash of t, right? All with their own dt. But can't I pull out that dt and do that? So now we have a formula for calculating a line integral written in a dot product format. You like? So all we need to do is tell you who all the various pieces happen to be, and you'll find that they make life a little bit trickier than you were hoping. Question 8 is a line integral written in differential form. This function, f of x, y, z, is going to be called sine x cosine y xz. Actually, they called it sine xi plus cosine yj plus xzk, but I hate that notation, so I just wrote it like that. And our space curve is going to be called t to the 4 minus t cubed t. And t is going to go from 0 to 1. So we're going to find this guy using all this information here. So let's see what that would look like. Well, it's going to be the integral from 0 to 1. This function times that guy's derivative plus this function times that guy's derivative plus this function times that guy's derivative dt. And right now, do you see that we've got a mixture of x, y's, and z's and t's? But if you're going to integrate, don't you have to have everybody in terms of t? What do you think is going to happen to, for instance, the sine of x? How will I change sine of x into t's? That's what I'm asking.
Would it be sine t to the 4th?
Correct. Times that guy. So I'll stick him at the front. Right. Well, the cosine of y will be this fella then, right? So that's going to be the cosine of negative t cubed. And at the front, there's going to be a negative 3t squared. So I don't want that anymore. And then the xz, well, isn't the xz going to be that guy? Sorry, xz is going to be that guy times that guy, which is t to the 5.
Times. Oh, because of the derivative.
The derivative is just 1, so none there. I'm going to have to split this guy into pieces. So I'm going to take that guy, and I'm going to take this guy. It really doesn't matter if I put the plus there as long as I put the negative here. And then that guy at the end. It's not uncommon that you have to take your integral and break it into pieces because they just get complicated. You're not always going to get a big polynomial, which you can do in one go. So let's talk about how we would solve each piece. Let's do this one first.
The first 2 pieces would be u subs, and then the last one would be just a normal integration.
Yeah, power rule. In this case, would you agree a u sub is t to the 4? And in this case, the u sub should be probably negative t cubed.
Yep.
Yeah, actually, it looks like they come out quite nice, don't they? Looks like if you do that u sub, let's show you this u sub. If you do this guy as a u sub, can you trust me that what you end up with is u sine u? What Calc 2 method do you use to solve u sine u?
It wouldn't be u because u sine times sine u because the
Oh, that
working the cube
disappears.
is the
You're right.
derivative.
I forget it. I'm wrong. But if that did happen, wouldn't you use integration by parts? But yeah, actually the u sub, you're right, takes care of that. Big horrible question, but it's just Calc 2 stuff. It's just time consuming rather than, I would say, anything else. Let's try another one of those guys. What's that? Let's do 10. At least a version of 10. The vector field is x. Oh, good. X, y plus 1. Also, it's not x, y, z at all. It's just x, y, so I'll rewrite that. So this is a 2-dimensional vector field. A little bit less work. Let's go. Our space curve. T take away sine t, comma 1 minus cosine t, and 0 to 2 pi. So that line integral is going to become the integral from 0 to 2 pi p times x dashed of t plus q times y dashed of t dt. That guy's p, that guy's q. So it's going to be the integral from 0 to 2 pi. You probably won't need anywhere near as many lines as I'm doing. If you differentiate this guy, you get 1 take away cosine t. And the other one is y plus 1. And if you differentiate this guy, where is it? This guy, you get positive sine t. And then x gets replaced by this. So you end up with a t take away sine t, 1 minus cosine t. And a y plus 1 becomes this guy plus 1. That's why, yeah, y plus 1. That's better, probably. So 2 take away cos t times sine of t dt. I better distribute this. What do you get? You get a t, a negative t cosine t, a negative sine t, a plus sine t cosine t. Distribute this, you get a 2 sine t and a minus sine t cosine t. If I've done this right, that gets killed off by that. This guy partially kills him off, and it looks like we are left with a t, a negative t cosine t, and a plus sine t. So all we need to do now is integrate that, which is pretty obvious, and integrate that, which is pretty obvious. But how are you going to integrate this guy?
That has to be an integration by parts.
Agreed? Integration by parts. And you're finished. Are we good with line integrals in dot product form? Right? We okay with the FDRs? Do you want to see another FDR, or can we move on to actually showing you what line integrals can give you in the physical world, what they tell you? Do you want to know, do you want to see another F dot DR or not?
I would like to see another FDR.
Then let's do it. Let's do one with a line in it then. So question 13. The function, I'm still going to do 13, but I'm going to combine what does a line integral give you as well. So, oh darn, it's going to be hard to draw, but I'll try my best. When you talk about a vector field, every single point in 3D space, right, has a vector associated with it, right? Now, since you can't draw an infinite number, but you can draw some. Can you imagine this is a 3D vector field? In this 3D vector field, there is an object, right, a space curve, r of t, traveling through it. Can you imagine that situation, right? So in 3D, every single point, can you think the wind is blowing in that direction or something? And this aircraft is doing its thing, right? The work done I think, did they phrase it by the work done on the field or by the field? I can't remember. I don't care. Right, the work done on this object moving through a vector field is the line integral f dr, right? So it's the guy that we've been finding. So see those numbers, if I'd got numbers, right? The 22 or the 45. Three things can happen. Numerically, this is a number, right? Three things can happen. You get a number like 5, right? You get a positive number. You get a number like 0, or you get a number like -4. Let's try and imagine what each of those situations might look like for an object. Can you imagine it's a magnetic field and something is moving through that magnetic field, right? If that is a positive number, that would mean it takes you energy or work to do that job, right? In other words, you have to push it a little bit more, right? What would 0 mean? So 5 positive number means you have to put in energy, right? Work to get the movement from the start to the finish. What would a 0 mean? What if the work done was 0? What would that kind of mean?
There's no movement.
Not so much no movement, but the amount of energy or work that it took would be balanced by the energy or work that you would get by the time you finished. Can you imagine a perfect world where you took a block and you shoved it up to the top of a hill, right? And then you tipped over and it slid on its own all the way down to the bottom of the hill. In a perfect world, would it not be a 0 work done story? Because the work going up, wouldn't you get that same energy because of it coming down at the other side? It would be a kind of balanced situation, right? Forces in get compensated by forces out. So the energy I had at the start would be the same energy that I'd have at the end. I might have to use some to get through tough bits, but I get a little bit of an extra movement or push at the end. And what would a negative one look like then? So if an object passed through a negative work done, what would Earth, because that can happen, what would it look like?
It'll look like the slingshot maneuver from 2010.
Right. In other words, you get energy out of the process, right? So you end up with more energy than you started. And work done, I think the units of work done can be converted into energy. That's the analogy I like using. So when we do these guys, you can get it. Now that now allows me to do, what was that number I said I was going to do? 13. So in question 13, we have our classic force field in 3 dimensions. And this time they're writing it the way I like them to be written. If you like every one of these questions to use I, J's and K's, just keep doing it. To me, there is no difference. You should pick what helps you best. And this is the force field. And what's the object going to do? It's going to travel from the point 0, 0, 1 in a straight line to the point 3, 1, 0. So I'll call that P and Q, although they don't. And it does one of those guys. And we've seen this guy a couple of times, haven't we? The straight line movement thing. Now, in this question, I have to create the parametric equation for C, because that's basically who C is. So the direction vector is P to Q. And so 3 take away nothing, 1 take away nothing, nothing take away is 1. There is that guy. And the R of T that we need, it's going to be 0 plus 3T, 0 plus 1T, and 1 minus 1T. Comfortable with that? Okay, let's put the package together then. The work done is that guy. In this case, it's going to be, there's my P, there's my Q, and there's my R. So it's going to be P, X dash T, Q, Y dash T, R, Z dash T, dt. It's going to be the integral from, 0 to 1, right? So 0 to 1. P is going to be x take away y squared. This guy's derivative is times 3. Then you've got Q, which is y minus z squared. And this guy's derivative is the derivative of that, so it's 1. And then it's R, which is z take away x squared. And the derivative of that guy is -1 dt. So I've replaced the P, Q, and R by what they are in terms of x, y, and z. I've replaced the x dash, y dash, and z dash from here, which ended up being numbers, which it would be in a straight line. And this is going to be x now gets replaced by 3t. Take away y squared, in this case, take away that guy, times 3. And the next one is y, which is t. Take away z squared, which is that guy. So it's going to be t, take away 1 minus t squared times 1. And then I've got z, which is this guy. Take away, this guy squared, which is what? 9t squared dt. Okay, just a couple of lines of tidying up here. Actually, I think I should do this one all the way to the end. So we're going to get 9t, take away 3t squared, plus a t, take away a 1, add a 2t, take away a t squared, add a t, take away a t, take away a 9t squared. What do I get? I got negative of them, negative of them, negative of them. So that's negative 13t squareds. I've got 9 of them, one more is 10, take away 1, that's back to 9, add 2 more, that's an 11. So I have an 11t. I got this guy kills off this guy, so that's all we have left. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Evaluate it at 0 and at 1. If you plug that in, you get negative 13 thirds times 1 cubed, plus 11 halves times 1 squared. Take away a whole load of nothings. I have negative 13 divided by 3 plus 11 divided by 12. And then I'm just going to do math number 1. And the answer comes out as negative 41 twelfths.
I
So
got a different number.
that's probably because I can't count. Where did I go wrong? I mean, just this bit is different, or anywhere between here and here?
I think you accidentally did 11 12 instead of 11 halves.
Oh, I did. That's an easy fix. So negative 3, there, almost did it there. Negative 13 thirds, that's 11 halves. Plus 11 halves, that's going to be positive now, which is also okay. 7 6. I can live with 7
That
6.
is what I got.
Right. Of course, check anywhere along here, because I may have a plus, it should be a minus. And the process is correct. In this case, this would require 7 6 units of work to do that journey through the force field. If this one had been correct, wouldn't the object have actually picked up some energy on the way through? It would have, and that may translate into all sorts of things. Sometimes the energy is transferred into it goes faster when it pops out. like the slingshot idea. But couldn't it also be it just got hotter? In other words, it picked up energy, but that energy became heat. What we know is that in one case, if this was the case, work would have to be done to make that happen. In the other, it would be that. You'll have to look up the notes, whether they talk about the work done by the force field or the work done to the force field. I don't know why that makes a difference, but evidently it does.